Let's learn how to write this electronic structure that we've learned about in a shorthand. We've learned that electrons are only in certain places around the nucleus, and we've learned how we can write these little boxes identifying the sublevels and orbitals that the electrons stay in. But writing out these little boxes is a pain, and it's orderly, but very inconvenient to use except for the smallest atoms. So what we can do is we can go and take these electrons and put them in a table that is much more condensed, or we can even make it easier to use a shorthand to express our electronic structure. I can actually draw an energy diagram where energy is increasing as you go up the chart, and then give the principal energy levels n equal 1, n equal 2, n equal 3, 4, 5, and 6, and then write down what sublevels I have within each one of those. There's an S sublevel in n equal 1, an S and a P sublevel in n equal 2, and an S, a P, and a D sublevel in n equal 3. I haven't written in the D, the P, and the D on this diagram yet because I'm going to keep this very simple for now. Within n equal 2, we have the S and P sublevel, and the S sublevels all have one orbital in them, but the P sublevel, remember, has 3. Now I have them stacked on top of each other. Even though they are all the same energy, we do that to conserve space in a table like this. So even though this one is higher than this one, it really is at the same energy. They all three are at the same energy. To write an atom that has 8 electrons in it, I just put electrons as arrows in the lowest energy places. And you can see I'm counting them up. And so now I have 4, 5, 6, 7, 8 electrons. This is identical to what we did in the previous slide. This is just another way of representing electronic structure. But this is rather cumbersome to draw a chart every time you want to think about where the electrons are. So we have another method of describing electronic structure, and that is with what we call our shorthand. If you look up here on the right, you will see I've written 1s with a 2 subscript, 2s with a 2 subscript, and 2p with a 4 subscript. The 1s is the sublevel, and the 2 indicates how many electrons are in that, which you can see there are 2 electrons in 1s. This says 2s with 2 electrons in it, and you can see 2s, 2 electrons in it. And then 2p sublevel with 4 electrons in it. 1, 2, 3, 4, and so I have a superscript of 4 electrons. And this is our most common way of representing electronic structure rather than using one of these charts or the boxes. This is a summary of all the different orbitals and their energy, and you can see that in n equal 1, all we have is an S sublevel. N equal 2, we have an S and a P sublevel, 3 orbitals in the P sublevel. In n equal 3, we have an S, a P, a D. Notice the D has 5 orbitals, all the same energy in the 3D sublevel. In 4, we have 4s, 4p, 4d, and 4f, each with the correct number of orbitals in each sublevel. Now, this is a very complicated diagram. We're going to go through this one time, but a few times actually. But what I want you to remark on right now is notice that 4s is lower than 3d. 5s is above 4s but lower than 4d. 5p is above 4d but lower than 4f. If electrons go to the lowest possible energy place, they will go from 3p and then next fill up 4s and then fill up 3d and then 4p and then 5s and then 4d, 5p, 6s, etc. This lends to giving a rather complicated diagram or electron configuration, but we're going to stick with the simpler elements and you won't be required to know all of the electronic structure of all of the elements. If I look at hydrogen, hydrogen has one proton, and when it's neutral, it has one electron. If I want to look at hydrogen and its electronic structure, I know that the electron has to be in the lowest possible energy place. So it would have to be down here in 1s. When I go to write the electron configuration of hydrogen, all I have to do then is write 1s and put a 1 as a superscript. If I look at helium, helium has 2 protons in it, so it has 2 electrons when it's neutral. That puts 2 electrons into 1s, one spin up and one spin down. When I go to write the electron configuration of helium, all I do is I write 1s and then put 2 as a superscript to indicate 2 electrons in the 1s sublevel. Lithium has 3 electrons, so 2 electrons in 1s, 1s2, 1 electron in 2s, 2s1. If I'm reading off this electronic structure, I would say 1s2, 2s1 for the electronic structure of lithium. For beryllium, with 4 protons, there are 4 electrons in beryllium, so 1s2, 2s2 is the electronic structure of beryllium. If I look at the superscripts and I add them together, you can see they come up to 4, which is the number of electrons in a beryllium, a neutral beryllium atom. Boron has 5 electrons, so its electronic structure is 1s2, 2s2, 2p1. Carbon has 6 electrons, so its electronic structure is 1s2, 2s2, 2p2. Nitrogen has 7 electrons, so its electronic structure is 1s2, 2s2, 2p3. Notice the sum of the superscripts adds up to 7 electrons in a neutral atom of nitrogen. Oxygen has 8 electrons, 8 protons, so in the neutral atom of oxygen, its electronic structure is 1s2, 2s2, 2p4. Fluorine has 9 protons and 9 electrons in a neutral atom, so its electronic structure is 1s2, 2s2, 2p5. Neon has 10 protons and 10 electrons, so its electronic structure is 1s2, 2s2, 2p6, adding up to 10 electrons total in the neutral atom of neon. If we skip ahead to potassium, you're going to see that there is a total of 19 electrons, and if you add these all up, you'd get 2 plus 2 plus 6 is 10, plus 2 plus 6 is 8, plus 1 more is 19. And you can see all the electrons are going to the lowest possible energy place. If I add 2 more electrons into this atom, one of them would go into 4s and one then would go into 3d. The order of these sublevel energies is given right here in this first line. But I don't want you to memorize that order, nor do I want you to use the rainfall method, which is sometimes taught in high school. I want you to use a periodic table to get your electronic structure. It tends to be a little bit less likely for mistakes to be made.
Be sure and do the in-text problems as you read. Now, for this part of the chapter, that we've just covered, these are the problems at the end of the chapter that you need to do. There are also worksheets and online quiz posted for this chapter. In the second part of this chapter, we'll look at how do you get electronic structure from the periodic table so that you don't have to memorize things, and we'll also look at trends in the periodic table.